as a starting point for this tutorial, you notice we went through the other ones pretty quickly. This is one that takes time, not because there's a lot of pages, just because they're just all the concepts take a while to kind of get the hang of. So we're going to spend several days on it. We spent half a day last time today, and some time next time as well. As a starting point, we want to just know what is the basic nature of this graph, of this shape here. I want to compare it to when you learned to graph quadratic functions. First, you had to learn what the basic shape looked like. You had to learn what the basic shape of this was. And then you could start to say, well, what happens if we add on 4, or what happens if we subtract 3 before you square it, and stuff like that, right? So first came, what does the basic shape look like? That didn't take too long because there was only one basic shape. Y equals x squared, you could say it always looks like this, right? There's a point there, there's 1 and 1 over here, and then 2 and 4. And that was the basic shape. Always the same. There was no variation on it. The problem here is that there's a bunch of different basic shapes, and we're going to look at what's happening with all of them. So it takes a while to get the hang of what the basic graph is. And then later today we're going to look at what happens if you start adding on numbers and subtracting numbers and changing things around. All right? So with that comparison in mind here, we hopefully got to the point last time to know something about this, that this is y equals 2 to the x. It's written over here, 2 to the power of x with that little hat thing. If you have something bigger than 1 to the power of x, it's an exponential function and it goes up to the right like this. If you change what that base is, it gets steeper or not so steep. So if I make this 3 or 4 or 5, you notice it's not really like it's vertically expanding, but it's getting steeper. It's not vertically expanding because this point's not moving, right? But it is getting steeper. The bigger the base number, the steeper it is, the more sharply it goes up. If I make the base 4.9 to the x, when x is 1, this is 4.9. This is always 1 down here. If I put this dot on here, that never changes whatever I do here, right? That point never changes. That intercept is that's the point you're going to work from with everything else. I want to remind you again about quadratic functions. When you were graphing quadratic functions, you learned that they look sort of like this, but what was a pretty important point for that graph? This one right here, the vertex, right? The vertex was an important point because then when you started moving it around and said, what happens if this goes this way? This became your reference point for when you started moving it around. When you start moving this graph around, this is going to be your reference point. Two things are going to be your reference point. The asymptote and that point. So when you start shifting this around, you're going to think, well, where does the asymptote go and where does that point go? It's more difficult because it's easier to see where the vertex of this is than this y-intercept here. But those are the points that we're going to work from. So it's important to realize that point is a vital thing to know. The y-intercept is 1, right? Or in other words, if you want to put a point, you could say the y-intercept is at that point, 0, 1. This is halfway through there on page 26. It has an asymptote whose equation is y equals 0. If I continue along this way, now I'm going to move it so you can see this a little bit better. Look at the y value here. As I make the x value get smaller and as I make it more and more negative. So as I go to the left here, this is getting more and more negative. It's headed for negative infinity. What's happening with that y value? Eventually it says 0, but that's only because it's rounding it off. It really is not 0. If I was to actually change this so that if they'll allow me to rounding, let's do 15. Why would they? Okay, well, whatever. There we go. Very useful. Oh, whoops, I got to put it way over here because I'm glad the x values to... Okay, now that you can't see the graph. Well, anyway, so you get the idea. Oops. So there's the point out there. Well, actually, we can just use the point, can't we? Because it shows the coordinates. There's the point. Whoa. put it down below there. And we will move it over. Glad I had this all organized ahead of time. There. Okay. All of that, maybe it's not worth it here, but if you go all the way to the right here, you notice the point is 0.000. Like if I keep going here, even if I zoom in on it or zoom out on it, that is going to get smaller and smaller and smaller, but never reach 0, no matter how far you go. This behavior is called asymptotic behavior. This is an asymptote. You had that idea in grade 11 for functions, but you usually had vertical asymptotes for functions. You remember those crazy functions that looked like, I don't know, it would go like this, and then suddenly it would go like this, and you'd have this dotted line here. That's an asymptote. In grade 11, you look for vertical asymptotes because when you have a function like 1 over x plus 2, you learn that the vertical asymptote happens at -2 because that's where it's undefined. I'm not really sure whether in grade 11 you truly understand why it occurs. And you didn't look for horizontal asymptotes even though that kind of a graph had a horizontal asymptote. That one had a horizontal asymptote at y equals 0. The reason it has a horizontal asymptote is because as you make the number more and more negative or more and more positive, the value gets smaller and smaller, right? Like if this is 1 over x plus 2, if you put in 1,000,000 here, 1 over 1,000,000 plus 2, that's like 1 over a really huge number. It's pretty close to 0, right? If you have a 1 in 1,000,002 chance, it's roughly 0. You got no chance, right? It's down to 0 almost. It's not quite 0. You still have a slight chance, but it's almost 0. It's the same idea here. If you have 2 to the power of negative, 1,000,000, if you go way out to the left, negative power, what is that the same as? A negative power is like 1 over that, right? 1 over 2 to the 1,000,000. Well, that's even less of a chance if that was a lottery. There you really don't. I mean, these are great odds, 1 in 1,000,000 compared to this. 2 to the 1,000,000th power, your calculator can't handle that. 2 times 2 1,000,000 times, it's way bigger than that. Anyways, that's what an asymptote is. It gets smaller and smaller. In theory, it never gets to 0, but so the asymptote is at y equals 0 for this. That's going to be important to know when you start moving it around. Hopefully you haven't scribbled the way I have on mine. But the domain and the range, if you look back at this, the domain and the range. The domain of this thing, now that I've changed it to whatever, 15 decimal places, the domain and the range, this point here, if you move this around, which it's not letting me do. Oh, come on. I thought I turned that off. Want to keep it rated G though. If you change that there, and I'm going to put it back to where it was. No, that's not what I want. I want to put it back to 1. Let's put it back to 1. No, to 2. And we'll put that point on there with my 15 decimal place accuracy. If you change this now, that obviously gets higher. If you change it to less than 1, that gets lower, right? It's going down to the right. Less than 1 going down to the right. Bigger than 1 going up to the right. If you have a number that's bigger than 1 to the power of x, of course it's going to get bigger and bigger the bigger you make x, right? You raise it to a higher and higher power. If you make this really big number, right, it's really sharp. If you make it on the opposite side here, really small number, it's going to be really sharp going down. If it's close to 1, like 0.9, it's just barely going to be going down. It's hard to even tell it's curved. And if it's just bigger than 1, it's going to be hard to tell it's even curved going up, but it is. Okay? The bigger you make that number, the more sharp the curve is. So maybe we can put that on here. The domain of this thing is all real numbers. You can choose, or if you like the symbols, you can choose any number for x. You can choose any number for x, and that expression is defined, right? Put anything in here. There's no restrictions on what x can be there for exponential expressions. If you like the symbols, you can write x. This is not an e, even though you probably said XER in grade 11 to remember what to write for domain. This means is an element of. So x is an element of. X is in the set of real numbers that are like that. I don't really care if you write words. I happen to like words better than symbols, but the range, though, is, what's the range here? Is it all real numbers? What kinds of numbers can't you get? Yeah, bigger than 0. Not equal to 0. It's never going to be 0. It's bigger than 0. That sticky keys thing threw me off totally here. The general shape of the graph. General shape of the graph. At this point, what you need to recognize is when b is bigger than 1, okay, when b is bigger than 1, the general shape of the graph is growth like that. It goes up. This is 1. The y-intercept is 1, but it goes up. I'm going to put the word growth here. Exponential growth. When b is less than 1, but still positive. That's all that means, between 0 and 1. Because you can't have a negative base here. It's undefined for most values. When b is less than 1, it goes down, right? I didn't draw it very well, but that's what it looks like. This is not called growth anymore because it's going down to the right as time goes by, or whatever it is. What is the opposite of growth? Decay. Very good. I know decay doesn't sound like it's the opposite of growth, but it is, right? When we talk about growth and decay problems here, whether we're talking about population, we're not talking about the people decaying. We're talking about the number going up or down, right? The people aren't growing. The people aren't decaying. I know you know that. Okay, the y-intercept is still 1, but it goes down. You could put in slopes down to the right, slopes up to the right, slopes up, slopes down. It's not a constant slope like a straight line, but it does have a negative slope the whole way, or positive slope, right? Positive slope. No, don't put that in there, but it's true. As b become larger and larger above 1, the curve becomes sharper, it's steeper. I don't know, steeper and sharper curve. Curves up more sharply, I don't know. This is part of the reason why people have difficulty with this, because you have to understand things where there's no numbers involved at all, right? It's just concepts about the graph. And in math, I think for sometimes people think, what? Do we have to know this? This is totally different, right? Maybe steeper wasn't the right word there, but I mean, we could say curves down more sharply, right? For this. It gets to 0 quicker, right? Not sure if that's helpful or not, but... Okay, so you have the whole sense of it. In your mind, a picture is worth 1,000 words, and probably a video is worth 1,000 pictures. So in your mind, if you have a video in your mind, I really think this probably helps, is this whole notion right here, just thinking about how the graph is different. When you have bigger than 1, less than 1, okay? Picture's worth 1,000 words, and a video is worth 1,000 pictures, so then the video is worth 1,000,000 words? I don't know. Okay, we got that? When it's 1, why is it a straight line when it's 1? 1 to the power of anything, right? 1 to the power of anything. When you put it at 0, you get this weird function where it only is on the positive side there along at 0, because 0 to the power of any positive number is 0. There's nothing on the negative side, because if you put a negative power there, the reciprocal of 0 is undefined, so there's nothing over here. If you made the base negative, which I can't do the way I set it up, there would be no graph anywhere. So we're only looking at positive bases. Okay? And that is that for part whatever.